Good day all, welcome to my channel. My name is Rodrick. In this video we are going to analyze a simple support beam with partially distributed load and a point load. We are going to start by draw the free body diagram, calculate the reactions, calculate the shear forces. Step 4, calculate the bending moments. And step 5, we are going to draw the shear force and bending moment diagrams. Let's jump into it. Step 1, here is our free body diagram with the reaction at the supports. At support A, we had a pin support, yes, that's why we have an horizontal reaction HA and a vertical reaction RA. At support E, we had the ruler, that's why we only have a vertical reaction RC. On the side, we have our sign convention for evaluating the bending moment and shear forces. So let's jump on step 2. That will be calculating the reactions. Calculate the reaction. Calculate the reaction. Calculate the reactions. Now our equilibrium equation. We got 3 equilibrium equation. That will be a sum of forces on the x-axis. Sum of forces on the x-axis is equal to 0. Sum of forces on the y-axis equal to 0, and sum of moment. In this case, we are going to take the moment at A is equal to 0. So these are our 3 equations. Let's set them out. On the x-axis, we only got HA. So it will be HA equal to 0 because there is no other force, there is no other element on the x-axis. We only got HA, so that will be equal to 0. So we have its value is equal to 0. And on the y-axis, we got a couple of forces on the y-axis, the 2 reactions and the applied load. So we do have RA is positive, plus RC, that will be RE. That will be RE. This should be RE. That will be RE and minus 15 times 8 minus 10 yeah, equal to 0, and sum of moments. So we got the moment at this point, so this becomes 0. RA and HA would be all equal to 0. The moment of those forces to the, because the distance from the applied load to the point of the moment is 0. So that will be the moment of those forces will be equal to 0. So we got now, it will be left with RC times 16. Sorry, I keep saying RC, it should be RE. Minus 10 times 30 minus 10 times 13 minus 15 minus 15 times 8 times 4 plus 2. Note that 4 is half of the length of the UDL and 2 is the distance from the end of the UDL to the point of moment. That also equal to 0. Let's call this equation 1 and this one equation 2 and this equation 3. Now, by solving these three equations, we are going to you have all our reactions. Let's consider first equation 3 because the easiest one. We only got one unknown reaction in that equation, which is Re. So we calculate that reaction. So equation 3 but Re equal to 10 times 13 will give us 130. We go 130 plus 15 times 8. I use my calculator quickly. 15 times 8, 15 times 8 times 6. 4 plus 2 equal to 6, yeah. So it gave us 720. And all this now divide by 16. This will give us 130 plus 720 divided by 16. Give you 53. So the reaction Re is equal to 53 125 kilonewton. And we can now solve equation 2. So equation 2, we got the Ra will be equal to minus 53 125. So it is Re. We got this value already. So I just punch it in the equation. Plus 15 times 8 equal to 120 equal to 120 plus 10. This will give us now 120 minus 53.125 plus 10. So this gives us now 76 875 Newton. Here is our reactions. Reaction at E and reaction at A. Now we need to jump on step 3 and calculate the shear forces. Step 3, will be shear forces. There we go. Now the shear forces we are going to calculate it from left to right. So we are going to take shear force at A, at B, at C, at D, and at E. This, and so on. So to get the value at each point, left and right of each of those points. So at A, shear force left of A is equal to 0. Left of A is equal to 0. As can as f of A is, there is no force here, so it will be equal to 0. And at shear force at A right is equal to the reaction at A, which is 76.875 kilonewton. Okay, let's go at point B. At point B, shear force point B left is equal to 76.75 because there's no other applied load between A and B, so it remains the same on that at the left of B. And it's also the same just right of B. It's also the same. Now shear force at C now. Shear force at C. At C left is equal to 76 what is 76 875 minus the distributed load, I mean this is actually the applied load between B and C, that we only have a distributed load there, which is 8. This will give you times 8. Give you minus. This is minus 43.125 kilonewton. Here we go. And then shear force at C right is the same as previous, 43.125 kilonewton. And shear force now at D shear force at D and length of D is also equal to 43 125 kilonewton, and at C, right, at D, shape was at D, right, we have now it will be 43 125 minus 10. Remember, 10 is that point node at D, because we're crossing the point node at D. We're crossing the point node at D, so that's why it minus 10. This now give you now 53 minus 53 125 kilonewton. Okay, that we got at D, left and right. Now the last point at support E. At support E, support E left is the same, is equal to 53 125 kilonewton, and at E now, right, is equal to 0. At E, that is equal to 0, because we're crossing the reaction there, which is 53, so it actually be minus 53 plus 53 is going up, it will give you 0. That's why the reaction, the shear force at the right of E is equal to 0. There we done with let's go down to step 4, which will be the moment. Step 4, bending moment. Bending moment. Oh, shut it. Yes, moment. It's a bending moment. It will basically be the same procedure, but this time it will be a moment calculation. Be a moment calculation. So moment at A, moment at A is equal to 0, is a pin support. Moment at A equal to 0, and moment at B at B is equal to, basically actually there are 76 875 times 2. Basically this is what it is. This moment, the reaction at A times the distance times the distance, which is 2 from B. So that's why I got so we are 76.875 times 2. This will give you 153. 153.75 kilonewton meter, and moment at C moment at C will be equal to 76.875 times the distance. I got 10. That distance is equal to 10. If you go back there, you will see distance from A to C equal to 10. 8 plus 2. This is how I got this 10, and then minus the distributed load, that will be 15 times the length of the distributed load divided by 2. This will give you 76.875 times 10 minus 15 times 8 squared divided by 2. The moment at C is 288. 288 minus .75 kilonewton meter. Now moment at D. Moment at D will be equal to 75 times 13 minus 15 times 8 times 4 plus 3. 4 is a half of the length of the UDL, and 3 is the distance between, remember, so the moment of the distributed load at point D, so we're taking actually from here to here. That distance will give you 4 plus 3. That's why I got that would be 7. This is where the distance comes from, and then you get 76.875 times 13 minus 15 times 8 times 7. Now this gives you 159. 159. 375. 159.375 kilonewton meter. Kilonewton meter. Now the moment at D, at E, which is as you can see at E, this moment actually got equal to 0. So but we do not prove it. It will be equal to 0. So this is actually a test that we are doing it right. Times 16 minus 15 times 8, 4 plus 6 minus 10 times 3. This should be equal to 0. Let's check that. 76, 875 times 16 minus 15 times 8 times 10 minus 10 times 3. Correct, is giving you 0. So we're done with the bending moment calculations. Let's go now and draw our bending moment based of these calculated values and shear force. So we start by first drawing the shear force and then draw the bending moment. Yes, our thing already set up. It just leave it off. Okay, let's just put it this way. Yeah. The shear force at B, we had it. The shear force at B is 76. Shear force at B is 76. Shear force at B. Let's change the color. So B 76 at A, the right of A is 76 and left of B also 76. So it will be let's take a straight line. Let's take a straight line here. It just this is not to scale. It's not to scale, so it just for illustration purposes. Line is Q. Let's do some. Okay. Take a line. Yes. And do. As I say, this only for illustration purposes. It's not to scale. This is what we got. From B to C, we got minus from B to C. At C left, we got minus 43125. 43125. So from now, is here. This is how it look like. Yes. And then here is minus 443 minus 43125, and here is positive, so it's changing from positive to negative. And at D left is also the same as shown earlier, as calculated earlier, also the same, so it's also 43. Yep. Now at D right is 53. D right is 53. Shear force at D right for minus 53, 125. So this bit increase. You go down here by 10. This is how it look like, and from here we go straight because it's the same. Here is our shear force diagram, and then here is minus, plus, and the value here is 76, 875. The value here is minus 43, 125, and the value here is minus 53, 125. We're done with our shear force diagram. Let's draw now the bending moment. Let's draw a bending moment diagram based on our calculated value. At A is 0, but at B is 153. So we go from here to, let me take a straight line. From here, we go to here. Yes. But on this, from B to C, due to the UDL, it's not a straight line, it's a curve. And remember that the maximum bending moment will be where the shear force is equal to 0. So it will be somewhere here. This is where our bending moment. In our upcoming video, we are going to mathematically find out the distance, the point at which the bending moment is equal to 0, and we're also going to find out the maximum bending moment value. We are going to do that on our upcoming video, and we will also going to, on the next exercise, calculating the point of contrafraction. So all those will be done on our upcoming video. So for now, let's draw this bending moment. It won't be that smooth, but I will try my best to get something nice. Yeah, this is how it look like, man. Not that straight, but this only for illustration purposes. Our maximum bending moment will occur here. This is where our bending moment is. Maximum bending moment is, yes. Here is here. And from here, the bending moment here at C is equal to 288 at C, and then at D it will reduce to 159. So it will be somewhere here, and then is a straight line. So that's, yes, that's our bending moment. And then the same, and from D to E, yes, also this is a 0, yeah. So that is our bending moment diagram. So we done with our diagram. This is plus, and it is plus. So that is done for now. Here's our bending moment. Here we got 159 here. What the exact value there? 159,375. 375. And then we got here 153.75. 153. Oh. So 153.75. And here we got 288. 288.75. Yes guys, yeah, we're done here. On that we were going to calculate this maximum value in our next video. Thank you for watching, and subscribe to my channel if you are not yet a member, and see you